Yeah, I think I'm recording now. Yeah, okay. So 1 minus px, and so you can take so it will be option D, 1 minus e to the power of beta 0 by beta x by this factor. So that is one, and the last question is on SVMs. So if you have so it was also referred to in the SVM lecture that suppose you don't have a linear class, you have a problem where the data points are not linearly separable, and then you have to do some basis transformation, which has also been called kernel transformation. So you do that, and then your model and then your data points suddenly become linearly separable in that higher dimensional space. So this is one such example where it shows that even if you select the kernel or if you expand the basis in a wrong way, then even after that a simple classifier, it will not become linearly separable. Okay, so let's plot the points here. So the data set becomes linearly separable. Okay, so this is the initial data point, these are the initial data points. One data point is at 0, one data point is at 2, and the other data point is at -1. Okay, and this and this, they are of class 1, and this is of class -1. So you have to separate -1, you have to separate this point and this point from this point, and that is not obviously possible by a linear classifier. So that is why you go ahead and you augment the data set by this. This becomes your new basis function. So then your data points are something like this. Your data set now becomes something like this. The first data point becomes 1 1, and the label is 1. The second data point is 1 0. Oh, this is 1 minus 1, sorry, yeah, 1 minus 1. The next point is 1 0, and the data point is 1, and the final okay, and the final data point becomes 1 and 8, and this is again 1. So now this becomes a two-dimensional problem. So let's plot it. So the first point is 1 minus 1, so 1 and -1, so somewhere here. The next point is 1 0, which is precisely this point, and the last point is somewhere 1 and 8, so somewhere here. And now you have to separate these 2 points from this point. Again, you see this is not linearly separable. So even after doing the basis transformation, you have not been able to separate out the two things properly. So the data set becomes linearly separable is obviously a false statement. So by graphical looking at it, by plotting it, you can see that they are not linearly separable. Yeah, so those are some very few questions that I could give. So now you can go ahead and ask me, is SVM clear, or do you have any doubts about the basic formulation of SVM? Now let's think about the dual formulation of SVM a bit later, because that anyway involves a lot of optimization tricks. I don't think that is within the scope of this course, but the basic formulation of SVM, is it clear to everybody? Or if you have any questions, you can go ahead now. Yeah.
Hi sir.
Yeah.
Sir, can you just summarize a little bit, sir, about that SVM and Lagrange constraint?
So the Lagrangian constraint, it will be difficult to understand, especially because you are not optimization is not a part of this course. But the basic SVM formulation, I will go ahead and I'll also do the Lagrangian part, but it is outside the scope. I should say that it is outside the scope of this particular course. Okay, so you take the dual formulation, you take it on faith that exists, but what I would suggest is for now at least the basic formulation should be clear to you all. Okay, so I'll summarize the basic formulation. So see, so yeah, so I think this was also the motivation behind SVM, I think was pretty clear from the lecture. So suppose we have data sets which are like this. Okay, data, so some classes are there like this, and the other class is here like this. Okay, so here what you want is you want your, so what is that you want? So you want to classify. That's the first question. The now the nonlinear part of SVM comes later. Now the first thing which I'll just talk about the linear part of SVM as of now. So now what you need to do is you need to find out this classifier. Now how do you want this classifier to be? So for example, for logistic regression will just learn this W and B. So let's say your classifier is W transpose X plus B. That is your classifier. So you want to learn this W, you want to learn this B, and this W and B you can learn in logistic regression in such a way that it will just classify. So it will find out some classifier and it will give it back to you. So that is one. The other way in which you can think of classifying is, I want this line such that the nearest point in the positive side and the nearest point on the negative side, and positive and negative I am talking in terms of classes. If you can make them, if you can maintain them at an equal distance from your line. So suppose this is your classifier and the closest positive sample and the closest negative sample, both of them are equidistant to you, then you call that to be a classifier. That also is a way of understanding your classifier, and this is a better way of understanding your classifier. Because why is it better? It is better because you know that all your positive classes and all your negative classes have at least this much amount of distance between each other. Okay, you are ensuring that by means of formulation of the problem itself. So that means your positive and negative classes have some margin. So so some amount of margin that you have between your positive and negative classes. Okay, so this becomes your margin. This is defined as the margin. Okay, in certain textbooks I think this half point is also sometimes referred to as margin, but I think this is the true formulation, that this is the actual margin. Okay, so this is the motivation behind why you want to go model your why you want to get a classifier by a different modeling technique. Okay, so that is the first thing. Then what you, okay, now one thing, okay, so then yeah, so suppose what you say is, you say you constrain your problem in such a way that this becomes W transpose. So suppose you have X plus all the positive samples, you have that, you do this, okay, and you force them to be greater than equal to 1. This is one constraint that you are putting on the problem. See, the other thing which you are when you are trying to find out such optimization problems, there can be so optimization problems you can have infinite number of solutions. Okay, and of course if your optimization problem allows you to have infinite number of solutions, then what you need to do is you need to constrain your space in some way. Okay, so these are just two constraints that people put on SVM. Okay, you could have thought of other constraints also, but these two constraints work well. So that is for positive samples. Positive sample means Y plus.
Sir, I have a question here, sir.
Yeah.
So this W transpose X plus B is kind of the logistic regression expression.
No. So I will come to that. Yeah. So see. Okay, let me give a side aside here. In machine learning, your input is X. Okay, your output is Y. Now what you have learned till now is, for example, linear regression. There you did W transpose X plus B. Am I correct?
Yes, sir.
And you minimize this loss. You minimize this loss, correct?
Yes, sir.
In logistic regression, I can't write this loss in such a space, but then you are not only doing just W transpose X plus B, that you are always doing, you are just taking a sigmoid function on top of that, or the logistic function on top of that, so that this lies between 0 and 1. Because your y also here lies between 0 and 1, your y actually belongs to the set 0 and 1. Correct?
Okay.
So this is the logistic function that you are referring to. In SVMs, you are again doing the same thing. You are taking some x, you are multiplying it with some w, you are adding that bias. That's, I mean, the overall overarching idea is always the same. You have some x, you have learned some w, you have learned some b, you multiply with x in this way, W transpose X plus b, and you get something. What result you get depends on the problem that you are trying to solve. Either you get a real value, I mean real value means a continuous value which can be anything in terms of when you are solving linear regression. When you are solving logistic regression, because of this sigmoid, you get a value of 0 and 1. For SVMs also, finally you will say that this either belongs to class 0 or class 1.
Okay, understood, sir.
Yeah. So these are the two constraints that you have put on the problem, and this also helps you combine these two in a very simple way, like W transpose X plus B is greater than equal to 1. So this is the first constraint that people have put on SVM. You can of course change these constraints, and I will talk about that a bit later. Okay. So that is the first constraint. So now if you see, okay. So now
So there x plus makes all positive values of x, right, sir? So when you say x plus
and x minus means two classes. So
okay.
This x plus is actually correlated with this y plus. So suppose you have a dog, as I come up with that example very often. So suppose you have a dog cat classifier. So your dogs can be plus, you can consider your dogs to be plus and cats to be minus. So that depends upon you.
Okay.
And whatever you do, yeah.
And no, go ahead, sir. I'll ask my next.
Yeah, okay.
So greater than or equal to 1 is just like simply they have taken 1, right?
Yeah. Because
okay.
I mean the one thing which has been referred to also slightly in the lecture is, so if you are taking greater than 1, so yeah, so one thing which is always true is this W and B you can select in such a way that, so suppose you had made it, suppose you had thought of something else and you had made this, let's say 100, instead of 1 you had made this 100. Okay, so your classifier will actually remain exactly the same. You will just change this scale, this W and B, and you will get the same and you will almost get the same. So for example, the example I think which was given in the class was 2x plus 3y plus something 6 equal to 0 and 20x plus 30y plus 60 equal to 0. So both of these lines are basically the same. So you will get, so you can either end up with this or you can end up with this. It doesn't matter from the SVM perspective which line you get. So why not make it 1 only, and that will make life simpler for us. Okay.
Okay, got it, sir.
I have a doubt.
Yeah.
Why have you used W transpose X minus plus B is less than equal to 1? It is the distance, right? Distance from the classifier to the point X minus, it has to be greater than equal to 1.
No, this is actually, so if you see, for example, okay, so let me, okay, suppose this is your line, this is one line. Okay, so you can define your W like this. Okay, so if this is W transpose X plus B, then W is always perpendicular to this particular line. Okay, so you can define your W like this. So if you see here that any point which is, let's say, here, for instance, any point which is, let's say, here, okay, I have to draw the coordinate system also, I guess, otherwise it might become difficult. Okay, let me draw it like this. Yeah, this is W transpose X plus B. I have defined W like this. Okay, and now suppose this is one x1 and this is another x2. So if so depending on the angle between this W and x1, if this angle is acute, then your distance will be considered as positive. If it is greater than 90 degree, then it will be considered as negative. This distance, what you talked about, this distance is not the true distance. If you think about the distance between 2 points is always positive, this distance is not like that. This distance is has some directional information also. I hope I am making sense. So
yes, perfectly.
Yeah. Okay.
You are trying to say that because the angle will become obtuse for x2, it will be negative.
Correct. Yes, precisely. Okay. So this distance is not that distance in that sense. So this is like, this has a directional component to it as well. So you can compute such things. So yeah. Okay. So where was I? Yeah, so now if you consider these constraints, so the first constraint, I'll rub this because do I have space? Okay, I have space. Okay, then I won't rub. Okay. Yeah, so you have these constraints. Now let's come to the margin formulation. So I have to draw a diagram here. Okay, let me try to draw the diagram as best as I can. Okay. Suppose your positive points are all here. Suppose this is your support vector. Okay. Okay, the points which are closest to the to your classifier are known as the support vectors. Okay, so that is a term. Suppose this is your classifier, this again is your W. Okay, this is the margin. Okay, suppose this is all that you have, and if I now draw this vector, let's say, and if I draw this vector, so this vector I am denoting as x plus, this vector I am denoting as x minus. I hope the diagram is clear to you all. And this line is this line, this particular line is x plus minus x minus. Okay, now what you want to do is, so now I will okay, now let me try to do this. Okay, so where am I? So I will draw this part of the diagram. So I have x, this is x plus minus x minus, and my W was something like this. So now the simple thing to do would be to project this. I mean, you want to find the distance in this direction of W. So what you need to do is, this is W. So what you need to do is, you need to figure this out. Okay, this will give you this will give you the distance between x plus and x minus when you are looking along W. So this will be the projection of x plus minus x minus on the vector of W, and this distance, of course, I mean, if W increases by a lot, then you would be thinking that, okay, I have a very good classifier because my x plus and x minus are separated out by a large amount of distance. So in order to account for that, you need to divide it by the norm of W. Is it clear till this point? Hello?
Yes, sir.
Okay. So if you have this sort of a thing, so now you get back to your equations. So you had already said that, okay, one more thing I have to mention here, that, yeah, so W transpose x plus B is greater than equal to 1 and less than equal to 1. They will be exactly equal to 1 at the support vectors. So that is another assumption that you want to make. They will be exactly equal to 1 at the support vectors. For all the other points, they will be greater than equal to 1 for the positive points and less than equal to 1 for the negative points. So if you know the support vectors, so that means you know that W transpose x plus B equal to 1 and W transpose x minus plus B equal to minus 1. You already know this by means of your assumptions. So you substitute this W transpose x plus from this equation up here. So W transpose x plus becomes 1 minus B and W transpose x minus becomes minus of minus 1 minus B. Okay, so this becomes by, okay, and this is of course by norm of W. So if you see here, minus 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 plus B gets cancelled out, so this just becomes the 2 by norm of W. And as I said, your entire motivation behind solving SVMs is to increase the margin. So you need to increase, so and this was exactly the definition of margin, right? So that is why you maximize over W and B, and you maximize this such that your constraints which you had taken always turn out to be true. Okay, so this is the basic formulation of SVMs. Is it clear till this point?
Yes, sir.
Okay, now maximizing something in denominator is a difficult problem to solve. So the simple problem to solve would be minimization of norm of W, and moreover you make it norm of W square. It will give you the same solution such that y of W transpose x plus B is greater than equal to 1. So this is your SVM formulation, the basic SVM formulation that we talk about. So this is that formulation. You don't, I mean, there are no difficulties till now here, I presume. So yeah, so that this is one. Now okay, so now there are two ways to look at it. First is how to solve this problem, that is the first point, and the second point is the soft formulation of SVM. So first maybe I will tell about how to solve this problem, and or maybe not, maybe first I'll talk about the soft formulation, because that I think is more intuitive and more understandable also. Then I'll talk about all those Lagrangian and all those stuff that goes on behind SVMs. Okay, so now here what you have done here is, now I will draw very simple diagrams, straight diagrams. Yeah, so here you had positive classes and here you have negative classes. So now there are two things. First is your classifier so first of all, your classifier may not be able to separate out all the points. So here in this formulation, what you are trying to do is you are trying to find this particular line such that all the positive points are on this side, that too by this amount of that too by this 1 by norm of W distance, and this is again all of them are away from this particular line by 1 by norm of W distance. Now that is a constraint that may be very hard to solve in certain problems. That is the first thing, that is the first problem that you might face in the basic formulation of SVMs. The other problem that might happen is, if you I presume we have some understanding about the nonlinear aspect of SVMs. So SVMs will go into some nonlinear space and will find out certain ways in order to separate out all the points perfectly. In other words, if you are able to do this, that means your training classification error becomes 0. If you are able to do this, and then you enter into the overfitting zone. Okay. So in order to stop that from happening, what we need to do is, you need to step back and ask yourself the question that, okay, I want the positive and the negative samples to be sufficiently separated out from each other, but at the same time I can live with certain errors. I don't want all of them to be correctly classified in the training examples. I can live with certain errors. Some errors I am fine with it. Now in order to account for that in your optimization problem, you come up with new constraints and also you come up with new so I'll tell how to do this. So the major problem what was happening was because of this. So let's talk only about the positive classifiers, positive data points right now. So I'll talk about them first and the negative data points will follow, right? So this was the situation that I was imposing on my problem, that all of them have to be greater than equal to 1. Now can you give me some idea about what I can do to relax this constraint a bit? So can somebody give an idea? I mean, any idea will do. So let's say I want this is xi means all positive components of I. So these xi's are all positives. So suppose this example, I want this constraint. Okay, I can live with this constraint not being held perfectly. So what can I do? So can you give me some intuition about what I can do? What is a way of relaxing this constraint a bit?
Error term?
Huh?
Error term?
Error term, can you, so suppose I add, I'll give you the answer first. Okay, suppose I add this. So what do you think if I, so let's say my xi I is equal to, my xi I is equal to minus 10. So when you have this value of xi I equal to minus 10, given that my objective is to relax this constraint, is this constraint relaxed?
No, I think it has become more stringent.
Why?
Because now W transpose xi plus b is greater than 11. You are further, separating the boundaries.
Excellent, yeah, correct. Now if I make this plus 10, so so now is the constraint relaxed?
Yes, now it is relaxed.
Right. So So is that argument clear for everybody?
Yes, sir.
Okay. So W transpose xi plus b, I will make my constraints to be equal to 1 minus I. Okay. And for, so similar, so this is for positive examples. These are for positive examples. Now let's talk about negative.
Sir,
Yeah.
question here, sir.
Yeah.
So when psi I is equal to plus 10,
Yeah.
even then 1 minus plus 10 is like minus 9, right? Even
Yes.
then, like greater than equal to 1 is better than greater than equal to minus 9. So again, we are increasing that boundary, right? Like
Right.
1 was
So
very minimal, but
yeah, so if you see here, so this was your line. Okay, suppose this point, this xi point, what I am talking about earlier was like this. You are understanding, right? This is the line that I am trying to find, and this is the point which I am referring to by this xi. Now earlier I had said that I want this line. So finally this is my final aim, to get this line. So earlier what I was saying was, I want this line in such a way that, okay, these are all the positive samples here, that this positive sample should be at least one distance away from this particular line, right? Now I am saying, when I am doing when I am doing plus 10, this becomes minus 9. So now I am saying that this point, this particular point can be minus 9, should be at least minus 9, its distance should be at least greater than equal to minus 9, which means that my line can end up here also, because here it is, let's say, minus 1. Did you get my point?
okay, getting.
So now your point actually is misclassified. So let me draw it again here. So suppose this is your point. Earlier what you were saying is, my line has to be here, because this has to be at least greater than equal to 1. Now you are saying that my line can be here, and this point can be here, and if this line is let's say minus 2, then this point is misclassified. But I don't care about that, because my constraint is allowing me to say that even for a positive point, my distance is minus 2, or my distance is not greater than equal to 1 strictly.
Okay. In that case, then that point will be classified as positive or
Negative.
sir?
It will be misclassified. It will be misclassified.
Okay.
Right. So for negative samples also something similar will happen. So for negative samples, you were having W transpose x minus plus b is less than equal to minus 1. So now what you want to do here is, you want to relax this constraint, right? You want to relax this constraint. So that means it has to be less than minus 1. So that means this has to increase. So now you add with sigma I. These are for negative points. Yeah.
Sir, here zeta is hyperparameter, or we have to like
no,
for each
zeta
point we have different
yeah, zeta will be part of your solution finally. The optimization problem itself will give you zeta. Okay.
Okay, just explain that how we get the
I'll come to that.
Okay.
I'll come to that.
Okay.
So
Sir, when we put this one question, sir.
Yeah.
When we put this constraint,
Yeah.
then there are chances that many examples could be misclassified.
Precisely.
Okay, sir.
So this is, I mean, I would like you to think of this zeta I as sort of a regularization. So for example, when you were learning linear regression, because of regularization, your training error was increasing. But you could live with that because you said that okay, if I allow this much amount of training error, then maybe my model will generalize better. So that is the precise thing that you are doing. You are not classifying all the training points perfectly. You are saying that okay, you have some room of misclassifying something, but you should generalize well. So as in regression or as in regularization of regression, here also this particular regularization will be controlled by a hyperparameter. So I will come to that. Okay. So,
Okay, sir. Thank you.
yeah, so you have these for negative points, and you have yeah, this for positive points. So again you can combine both of them and you will get something like this. Yeah, you will get something like this. Okay, you multiply the first one by -1, the second one remains as it is. So this becomes your constraint now. So your formulation before was what? Minimum of norm of W square over W and zeta I and B such that yi into W transpose xi plus B is greater than equal to 1 minus sigma I, 1 minus zeta I. Okay, so you do this, you solve this problem, and you will see that SVM does not work. Okay, and one more thing is zeta I must be greater than 0. So till now what the problem is, I will rewrite it here. Norm of W square, I am not, okay, I will write it anyway, such that yi W transpose xi plus B is greater than 1 minus zeta I and zeta I is greater than equal to 0. This is your problem till now. Okay, now you solve this problem, and what you will see is, okay, so now what do you think if you give this problem, then what will happen? First of all, okay, let me ask you this question. What is the minimum possible value of norm of W square? Hello?
0.
Yeah. Right. So this is the minimum value of 0. So it cannot go down below 0. So this, if this becomes 0, that means a vector whose norm is 0 means it is 0. So this is 0. That means you have yi into some B is greater than equal to 1 minus zeta I. Okay. So suppose you make zeta I go to infinity. Suppose, let's say your zeta I becomes a huge number. So what does that leave you with this? Where does that leave you with this constraint? So zeta I goes to infinity means this constraint is already accounted for. This constraint is accepted because zeta I is a very large positive number, and and suppose your optimization problem once, because your optimization problem will always try to reach the minimum possible value. So suppose your
sir, are you writing something, sir? At least the screen is for me.
Is it? I'm writing something now. Is it? Can you see?
No, sir.
Is it true for everybody?
We can see, sir.
Okay, then you can just rejoin, whoever is having that issue. Hello? Yeah, I think she is rejoining. Okay. Okay, where was I? Yeah, so the first thing is clear, right? That zeta I can go to infinity. Your optimization problem doesn't have a problem with this because this zeta I greater than 0 constraint is accounted for, is adhered to, and if you have zeta I going to infinity, then this becomes a very negative number. 1 minus zeta I becomes a very small negative number, and you can always find out some b, and you can also set w to be 0 such that this is always true. For example, you can set b to be 0 and w to be 0 for all cases, and even then this constraint will be satisfied. Is everybody with me?
Yes, sir.
Please repeat, sir, just what you said.
Yeah. See, if you just give this problem, then your optimization problem always tries to find out the minimum possible value. Now you yourself said that the minimum possible value of w square is 0. Now I am saying that I will make w 0, I will make b also 0. Even then all these constraints will be satisfied. Am I correct? Because zeta I is a very high positive number. So 1 minus zeta I will be very small. So 0 will obviously be greater than that.
Yes.
So this constraint is satisfied, right?
Yes.
So that means this constraint is satisfied, this constraint is satisfied, and your optimization problem is quite happy to give you the answer of 0. So you solved all this problem to finally say that your w is 0 and your beta is 0. So that makes no sense at all. So where did we go wrong? So where did we go wrong is, first, from the mathematical point of view, this term 1 minus zeta I cannot be arbitrarily small. You have to do something to stop making it so small that everything goes to, that w and b both go to 0. That is the first thing. The other thing is from an algorithmic point of view. So zeta I being positive means that you are accounting for more and more errors. Now if you account for more and more errors and your zeta I becomes so large that you have misclassified all your data points, then basically you have nothing, you have learnt nothing. So the only way you can stop this from happening is to constrain the value of zeta I. So that is why you add these you modify the problem like this. Now what will happen is, if you are arbitrarily increasing zeta I, then this constraint allows it, no problem. This constraint will also allow it, that is also not a problem, but your objective function will start increasing. If your objective function starts increasing, then your optimization problem will have an incentive of also not increasing zeta I too much and also not reducing zeta I to all zeros. That's the job of the optimization problem that you will solve. And this C is a hyperparameter which tells you how much regularization you want, or how much amount of error you can live with. Is it clear how the soft formulation of SVM comes about?
Sir, can you just repeat this when you told, I mean, the value of C? I mean,
yeah. Okay, so so one thing is, so see this zeta I which I am talking about. So zeta I means that you will have some errors in your training data. That part is clear, right?
Yes, sir. Yes.
Now, if you so that is why in any, for example, again that is why I talked about regularization first. So in regularization you had that parameter lambda. So you wanted that lambda, you could choose that lambda depending on your performance, depending on the validation set performance. So similarly here also you can't just C gives you a way to to say that okay, this is the amount of training error that I will live with. If you give me any more training error, then that is not acceptable to me. So C gives you the relative strength of how well you want to classify, or how good your margins are and how much amount of training classification error you can live with. So that is the value of C.
Also my confusion point, C into summation of sigma I, how C is controlling that
yeah,
the minimization.
Right. So let's say you make C infinity or a very large number, then what do you think zeta is will come up to?
Zeta is positive, so any number, so
no,
again
zeta
whole term is
no, zeta is greater than equal to 0. So
any positive number, yes, 0.
So
zeta is greater than equal to 0 means positive any.
Yes. So so in the range of 0 to infinity for zeta i's, when C equal to infinity, can you think of one number such that this minimize? So at the end of the day, you always remember that your problem will try to minimize this value.
Minimum value is 0, you are saying that.
Yes. So all the zeta i's will turn to 0 when C goes to infinity, correct?
But zeta is a tolerance, no, sir?
Right. So what does that mean when zeta I goes to 0?
Means our line is that itself.
Yes, you are back to the original formulation.
Yes.
Now let's say your C becomes very small. Your C is very small. You don't. So C is 10 to the power minus 10. Let's say. I mean, you will never put such values, but suppose 10 to the power minus 10. Then what will happen is your zeta I can increase, because even then the loss won't increase that much. So now you will be incorporating more and more errors in the training data.
So C we will decide based on how zeta I.
No, C you will decide based on the performance on your validation set. C is just like any hyperparameter.
Okay.
Zeta i's will come from the solution of the optimization problem. Zeta i's will be given to you by the optimization problem. You don't need to think about how zeta i's are coming to you. But what I am trying to say here is, you can understand how to change the value of C depending on how this optimization problem will generally be solved. For example, when C goes very high, when C is very high, a problem which is trying to minimize your value will always try to, it will always see that C is so high, that means I have to make zeta is very low, otherwise this optimization value will increase by a lot. Similarly, when C is low, then it can make W close to 0. When C is very low, it can make W very close to 0, and even if it increases zeta I, the value will not increase because C itself is very low, all the constraints are satisfied, and you are happy. I mean, the optimization problem will give you a value of W which is almost close to 0. Am I clear?
Okay. So when we implement, so how the C we are giving,
yeah, so that
get the idea of that and that value. That's
yeah. So that depends on your. You will always have a validation set. So you train a SVM with some value of C. You see your you say your training set performance. You see your validation set performance. If you see that there is a large gap between the two, then you need to increase. You need to decrease your C slowly. Okay. So I will write that. Suppose overfitting. Model is overfitting. I hope this overfitting term, I am not describing what overfitting here means. Then you have to decrease the value of C. Okay. Is it fine?
Okay.
Yeah. So treat this C exactly in the way how you treated lambda in y minus W transpose x plus b whole square plus lambda of, let's say, W transpose W, I am not considering b, plus lambda. I mean, this is the way you had regularized regularized linear regression. So the way you had treated this lambda, treat this C in the same way, nothing else. Okay, so yeah, so that is a soft formulation of SVM.
decreasing of C will be hit and trial, or what? How we can determine?
Yeah,
that?
more or less hit and trial, you can say.
Okay.
But you will, at some point of time, you will see that if you continue, I mean, if it's it will give more or less similar values at 100, it will give similar values at 10. So then you will know that you have reached more or less the correct C you have reached.
Okay. And regularization parameter we call as a whole term, or C only, or zeta only? Regularization
Zeta is not regularization.
Okay, it is just the margin. Okay, tolerance.
It is just the tolerance.
Tolerance.
So I would not suggest that you call this as a regularization term. Okay. I would ask you to think of this as a regularization term. That will be helpful.
This whole process is right. Overfitting.
You are trying to avoid overfitting. Okay. So yeah. So I hope this was clear.
Sir, the C is a regularization, right, sir?
Regularization parameter, yes.
Parameter, yes. That's
the hyperparameter. It's a hyperparameter for you. Yes. Okay. Yeah. So now coming to the most difficult part of SVMs is how to solve these problems, right? So for solving the problems, maybe the best way to solve the problem is to not go through this C business, just get the original formulation of SVM and see how it is solved. So the problem was W and B, norm of W square such that Y transpose sorry, not Y transpose, Y I this was the problem. Okay. So now there are certain things that I mean, there is something known as a Lagrangian. So this this constrained optimization problems come with many tools for solving them. So one of the tools is solving the Lagrangian and then going on. So this is also known as the primal problem. So primal problem is the actual problem that you are worried about. Okay. So sometimes there is another way of looking at the same problem, which is the dual problem, and that sometimes gives you a better way of, I mean, sometimes it will give you an easier way of solving the same problem. Okay. So I mean, I know these things are not taught in this course, and these, I mean, just take it on faith that there is something known as Lagrangian. So the Lagrangian would be, it will include another constraint alpha. So okay, so so one thing that you should remember always is, suppose you have a, okay, let me not draw this here. Yeah, suppose you have a problem, minimization of x, I'm giving a general formulation here, such that gx is less than 0. Okay. So if this is the formulation, then the corresponding Lagrangian becomes, okay, yeah, the corresponding Lagrangian becomes fx plus alpha times gx, where this new thing of alpha must be greater than equal to 0. Okay. So this is one of the formulations of, this is one of the ways in which you can think of how you can solve constrained optimization problems. So here the constraint is slightly different. Here the constraint is W transpose xi plus b is greater than 1. In order to put it into this particular format, what you need to do is minus yi into W transpose xi plus b plus 1 is less than equal to 0. And now you can apply this Lagrangian thing. So your Lagrangian now becomes, I will write norm of W square as W transpose W, and this becomes, okay, minus alpha I yi W transpose xi plus b minus 1. Okay, so this becomes your Lagrangian. Okay, so then what you need to do is these are certain steps which are all part of optimization theory, but now you have to take it on faith that this is the way you need to solve. So now you do two things, you do these two things. Okay, so the it's very difficult to go through this without going through the optimization basics. Anyway, so see the primal problem in your
yeah. Can you give a intuitive or visual picture of that Lagrangian things that will help?
No. That
mathematical part is I can go through that understood, but from where the idea institution is there.
Yes, that itself requires you to go through an optimization course. Okay, the way these things work is,
I think any expression could be, we can give some visualization if you understood correctly. Like in any simple example, like in x square or less than some.
Okay, let me think of that. Maybe right now I can't think of a very simple explanation of this, but let me try to give it. Maybe next class I'll try to give this. Okay. I'll keep this in mind, but I don't think there is a very simple explanation for all this.
Okay, further steps are, I think we will partially derivative and put it 0 like that.
Yes. So you will just take the derivative of dou L by dou W. So yeah, so where I was coming was, see, so one thing is, so the primal problem is this is the primal problem. Here your values are W and B. You want to find out W and B, and if you see the way the Lagrangian is defined, you have introduced a new variable which is alpha, which multiplies your constraint. So which multiplies this constraint here. So in your dual problem, your alphas will become your decision variables. So these are known as the decision variables. Okay, so yeah, so one way in which you can think of this
problem. Can we say that we are just augmenting the function with the constraint, that linear combination of constraint also we are adding into the main function which we wanted to optimize.
Yeah, so let's say one way in which you can look at this, this is some very loose graphical way of looking at this, but okay, this is a very loose graphical way. I'll just draw it to make you understand. So suppose this is the function that you are trying to minimize, okay, and this is the primal problem. So your dual problem will be something like this. Okay, so
saddle point concept you are talking?
No, not saddle point. So saddle point is if the entire function was like this. So what I am trying to say here is, you are trying to solve, so Lagrangian is just a tool. Okay, Lagrangian is just a tool from going from this problem to this problem. This is the primal problem.
Okay,
and this is the dual problem. So you will always see that if you are minimizing the primal problem, you are maximizing the dual problem, because ultimately your point of interest is this. So if sometimes it will be easier to go from to go through this path, sometimes it will be easier to go through this path.
Yes.
So depending on the ease of the optimization problem, you will either solve the primal problem or the dual problem. Now there is one more caveat here, like these are all convex functions. So some convex shaped functions, let's talk about, let's think that they're just convex shaped functions. So for convex functions, this is true, that if you solve the dual problem and you solve the primal problem, then the solution of the dual and the primal problem will always be the same. That is known as strong duality. Okay. The other case would be that your there might be cases where your dual problem will actually lower bound your primal problem. So your primal problem will actually you might never reach to that problem, never reach to the solution which is predicted by your dual problem. Okay, so that is also possible. I mean, there can be functions, strange functions also, that where the primal and the dual problem won't have the same solution, and in that case that is known as a weak duality case, where there will be a duality gap between the primal and the dual problem. So all these are details. I mean, I don't want you to get involved in all these, but just remember that for SVM at least, if you solve the dual problem, the solution that you will get is the same the solution that you would have got if you had solved the primal problem.
Okay.
Okay, so that is the only takeaway.
So this duality statement are given by Lagrange, or that concept is different, or this?
No, it comes from Lagrange only. Lagrange is just a tool which helps you move from the primal problem to the dual problem. So obviously the relation between the primal and the dual problem will also be dictated by the Lagrangian itself. Okay. So these are very interesting things, but I saw that it was not taught in the course also, so it's fine. I don't think they are expecting you to know all these also. Okay, so yeah, so as I said, Lagrangian is a tool to go from the dual problem to the primal problem. So that is why you need, so this was your problem, right? This was the Lagrangian that you were trying to solve. This was a Lagrangian that you were trying to solve, and now you just replace this W. So you just replace this W by means of this alpha. W and B has to be replaced by alpha. So you solve this dual W equal to 0, you will get something, and what will you get? Okay, let me also put half here, doesn't matter. So if you get half here, then this becomes W minus some okay, this is okay, this is element wise, so this becomes alpha I yi xi, okay, equal to 0. So your W becomes summation of alpha I yi xi. Similarly, you take dou L dou B equal to 0, and that way you will get what will you get? Summation alpha I yi equal to 0. Correct? These are the two equations that you will get. Yeah, these are the two equations that you get, and you put it back here. So now you replace all the W's by this summation. You replace and you use this alpha summation of alpha yi, and if you do that, then what will happen? The first term is half, and this is W transpose. So W transpose means this is alpha I yi xi transpose, and another W. So I will use another script here, alpha j summation alpha j yj xj. Okay, this becomes summation alpha I yi. So again I have a W transpose here. Okay, again I have a W transpose here, so I will again have this term alpha j yj xj. Okay, this is summation, and this is minus summation alpha I yi b plus summation alpha I. Okay, so okay, first of all this goes to 0 because alpha yi goes to summation of alpha yi goes to 0, and this minus half and this plus half and this minus becomes minus half. So finally your problem becomes, and as I said, if you saw here, So if you are minimizing the primal problem, you are maximizing the dual problem. So now everything is in terms of your dual variable. So you need to solve for max of alpha I such that this is summation of alpha I minus half of summation I summation j. You have alpha I alpha j yi yj and xi transpose xj. Okay, so I hope this is correct, right? So this becomes your dual problem, and now you solve this. So immediately certain things you can okay, this is your dual problem subject to some constraints. Yeah, so your first constraint was alpha I was greater than 0 such that alpha I is greater than equal to 0. That is the first constraint, and the second constraint is alpha I yi is equal to 0. Okay, these summation of alpha I yi equal to 0. So that comes from here, and alpha I greater than 0 is actually, it comes from something known as the KKT condition. So alpha I has to be greater than 0. That is the only thing that I would say as of now. Okay, so this is one. So now, so why did you go through all of this to solve your problem? I mean, you could have solved the primal problem. So why is the dual problem simpler? So first of all, you see here you have alpha i's as your decision variables. There you have w and b as your decision variable in the primal problem. So how is w and b related? Let's leave b, let's just concentrate on w for now. So suppose x is 100 dimensions. So what will be the number of w's present? Hello?
Can you repeat your question, sir?
Yeah, I am saying that suppose your x is 100 dimensions. How many w's will be there? How many w's you need to find out?
I think 1 w with 100 columns.
Yes. So basically I am talking about, when I am talking about w, I mean w1, w2 and so on, w100. So you need to find out these 100 numbers. And so that will give you your problem, that will give you your solution. But here what you see here is, it depends on the number of data points, because alpha I actually multiplied your number of constraints, and your constraints was defined for each data point. So therefore the number of variables here would be n, which is the number of examples. And here it will be the number of dimensions. So of course in most cases what will happen is your number of examples will be much more than the number of dimensions, right? So that is the way that you have seen, so that you will have maybe 10 dimensions and 100 examples. So that tells us that probably we should stick with the primal problem. Now therein comes a catch, and that is where the reason why you have gone to this particular problem of, or this particular way of solving the problem, you went to all this duality and all those things, because of one possible way, because of one thing only, and that is, if you see here xi, the way xi is represented, or the way this training sample comes in your formulation is in the form of xi transpose xj. The way it had come in your original formulation, it had come here, it had come in your constraints, and only xi was here. So if xi was so just note this difference. And now let me give you an example. I'll give you a very simple example. I think something similar was also told in the class. So suppose you have a function x1 x2. Okay, you have a two-dimensional thing. You have x1 x2 and you transform it into some space. Somebody comes and tells you, you transform it into this space, which is root 2 times x1 x2. So given x1 x2, you have moved to this particular space of x1 square x2 square root 2 x1 x2, and then so this transformation, let's say, is represented by phi, and now you do phi of x transpose phi of z. You do this. Okay, so what does that come to? x1 square x2 square root 2 x1 x2, right? And phi z becomes z1 square z2 square root 2 z1 z2. What does this come to? This comes to x1 square z1 square plus x2 square z2 square plus 2 times x1 x2 z1 z2, which is nothing but x1 z1 plus x2 z2 whole square, which is nothing but x transpose z whole square. This is simple stuff. The only thing that I want to tell you here is, suppose you had, so when you are actually doing xt z square, remember these are all in R2. xt and z are both in R2. You are taking two vectors in R2, you are computing a dot product between them and you are squaring them. In effect, you are doing a dot product in 3-dimensional space. Is this clear?
No sir, can you repeat your last point, sir?
Yeah, so here xt and z are both in 2 dimensions, correct?
Yes.
So I am doing xt transpose z whole square. So I can say that that is this. Xt transpose z whole square is x1 z1 plus x2 z2 whole square. Then I expand it out like this. This in effect can be written as this dot product. Am I correct? This is same as this.
Yeah. Yes sir.
So what is the dimension of these vectors?
3 dimensions.
Right. So what you are effectively doing is, you are taking a dot product in 2 dimensions, you are just squaring them, right? You are taking a dot product of 2 vectors in 2 dimensions, you are squaring them, you are effectively doing a dot product of some transformed versions of those vectors in 3 dimensions.
3 dimensions.
So just in 2 dimensions, you are able to do something which is actually a dot product in much higher dimensions. Okay?
Okay.
So that gives you a way of handling high dimensional problem. Now why do you want to do high dimensional problems? First of all, your xi and xj may not be separable in low dimensions. You need to go to higher dimensions, you need to add one more axis, let's say, in your data points, so that one more dimension in your data points, so that they become linearly separable. SVMs cannot do nonlinear separation. Nowhere here have I considered anything which is nonlinear in any way, right? Everything was linear. So the only way you can hope to solve a problem which actually can be separated only in a nonlinear space using SVMs is to transfer xi and xj in such a way that in that high dimensional space your problem becomes linearly separable. Is the motivation clear for why we wanted to go to high dimension space?
Sir, can you repeat?
Yeah. So let's say I have let's say I have points like this. Okay, I have points like this, And so what do you think? Are these, I mean, these are the two classes, so are they linearly separable?
No, sir.
Right. So now what I do is I take this x and I augment them by x square also.
Yeah, so that we get in a high dimension, we can linearly
so now
separate.
This becomes here, this comes somewhere here, this is somewhere here, this is somewhere here, this goes up to here, this goes up to here. Now you can separate it out by this line. Is it clear?
Yes, sir.
So now here what you explicitly needed to do was you needed to move this x to x square. Now suppose it was not even separable in x square also, then you would have to do it, let's say x cube, x to the power 4 and so on up to x to the power 100.
Okay.
Even then you saw that it is not linearly separable.
Right.
Then what you need to do, you need to go up to x infinity. That is the maximum that you can go to, right?
Yes, sir.
But you can't really calculate x to the power infinity. I mean, you can't take x, compute it to the power infinity, and so you can't do that, right?
Yes, sir.
So this is one way of transforming your x and going about SVM. That is one way, but that of course gives you a constraint that you can't go up to above a particular level.
Limitation, threshold.
You have a limitation. What this tells you is, no, you just do x transpose z to the power of 1000. This is still R2, this is still R2. This is just a number, this is a scalar. X transpose z is just a scalar, right? If you take it to the power of 1000, you will still get a scalar value.
Yes, sir.
That in essence is actually doing a dot product in 1000 dimensional space.
Yes, sir.
Got it? Now.
1001 dimension.
Huh?
It could be more than 1000 dimension.
It could be more than 1000 dimension. It could even be infinite dimensional.
Okay.
So for example, there is so these functions are known as kernels. Okay, these are known as kernels. And now, so one thing, so now so infinite dimension is just an example. I'll give you that example also, that is fine. But why I wanted to tell this was, okay, so now kernel gives me a way that, okay, I will take a dot product in low dimensions, I will do something with it that will actually be equivalent to a dot product in a much higher dimensions, much higher dimension. That is what kernel is telling us. But how can you use that? It's very difficult to use that. Why? Because you see, in the optimization problem, in the primal optimization problem, your x was sitting here. So kernel gives you a way of doing taking dot products, and that dot product you will do in low dimensional space, that will give you something in the high dimensional space. That is actually equivalent to a dot product in a high dimensional space. But here xi is sitting alone. So here xi, if you have to go to a high dimensional space, you have to make this xi, you have to transform xi like x1, x square, x cube, x4, x to the power 5 and so on. That is the only way you can increase the dimension of x in this particular primal problem. Luckily enough, and that is what people, I mean the genius of people who solved this problem came, they found that in the dual problem, xi appears nowhere, not here, not anywhere here, xi appears only here, and that too all data points are appearing in the form of dot products. So here now what you can do is, in place of xi, you take your kernel functions, you do this dot product, and that is equivalent to a dot product in the high dimensions. Got my point?
Yes, sir.
Okay, so that is the reason why you went to all that trouble of solving for going to the dual formulation, because in the dual formulation you can now use kernel functions, and kernel functions will transfer your x all the data points to a much higher dimensional space where the problem might be separable. Okay. So one
Sir,
more.
what is the difference? What is the difference between Gaussian kernel and polynomial kernel, sir?
Yeah, so polynomial kernels is one example is just here. So polynomial kernel is something like this, x transpose z to the power of d. Okay, and I think the Gaussian kernel is the same as the RBF kernel. I might be mistaken, but so the RBF kernel, I think that is the Gaussian kernel.
Yeah, it is RBF, but both are like non-linear kernels only. So not little confused, like what is really the difference between both?
Yes. So the Gaussian kernel or the RBF kernel is something like this, right? 1 minus 2 sigma square summation x minus z whole square. Correct. This is square. 1 by 2 sigma square into summation of x minus x whole square. You can understand, right? This is the polynomial kernel and this is the RBF kernel. Correct?
Yes, but both are like non-linear only, right, sir? So
now
is it
right? So what is the expansion of this function? I mean, what is the expansion of this function in the sense that it is a finite series or infinite series? I mean, this is just e to the power x. E to the power x is finite, is it? What is the expansion of e to the power x?
The complexity which is in the order of exponential, something like that.
No, I am saying that what is the expansion of e to the power x?
Okay.
So it is infinite. Okay, there are infinite terms. It is e to the power x has infinite number of terms in its expansion. Okay. Now can you guess what is the difference between RBF kernel and polynomial kernel, given that I showed you this? Okay, I'll tell.
okay? Because polynomial has only finite numbers and
exactly.
RBF is infinite.
Yes. So for any polynomial kernel, I might work for a year, but at the end of the year, I will be able to give you these representations, that this polynomial kernel was found out by expanding your x into these many dimensions. Maybe it might maybe 1 lakh dimensions, but somebody will be able to tell you that if that by means of computing this polynomial kernel, you are actually doing a dot product in 1 lakh dimensional space, right? For RBF kernel, nobody will be able to tell you what is the dimension of the space where if you do a corresponding dot product, you will get the value of the RBF kernel, because it is actually infinite dimensional space.
And probably the time taken will also be.
No, it won't be increased. That's the beauty. It won't be increased. What will you do? You will take x, which is in R2, you will take z, which is also in R2, you will compute x minus z whole square, then you will take exponential of, so why will the time increase? This can be solved by your calculator also.
So in that case, like RBF kernel is better than polynomial kernel, sir?
Yes, of course.
Okay.
So what I'll write here, what I was saying, so RBF kernel implicitly doing a dot product in infinite dimensional space. Polynomial kernel implicitly doing a dot product in finite dimensional space.
Sir, what about this linear kernel?
All of them will be linear kernel. All of them would be in finite dimensional space. Only RBF kernel and some others maybe. Not only RBF kernel, only some other kernels can also be designed where they will do it in infinite dimensional space. I mean anything which has expansion which is not finite is actually doing a dot product in an infinite dimensional space.
Okay, sir.
Sir, I've heard even about this linear kernel, sir. So
Yeah.
kernel is only used for like to get that non-linearity in that higher dimension, right? So
Yeah,
why
so
is it
not
again called linear kernel?
so not necessarily. For example, okay, let's say you have. So I will always ask you to not say that it is always higher dimensions. Okay, so suppose your points are something like this. So these are your all positive points and these are your negative points. You do some transformation, you stay in the same dimension, but now your all positive points lie here and your negative points lie here, and then you linearly separate. What is this transformation that you have done from here to here?
Same dimensional transformation.
But can you
Linear transformation.
no, can you give me a name about this transformation?
Squaring.
Distance we are taking. RBF you are going to say?
No, RBF will move it to IB. RBF I can't draw. So RBF is going to infinite dimensional space. I am saying that what is this transformation that you are doing?
Distance we are taking like in radial direction.
Yes, precisely. So this is the radial transformation, which is the polar transformation.
Yes.
So you are taking that and you are converting your model into and you are still being able to separate out the points. But in SVMs it's always I mean linear kernels, okay, I don't think they are ever used. I mean for simple problems maybe they may be used, but they are almost generally never used. RBF kernels and polynomial kernels are generally the most used ones.
Okay, sir.
Yeah. Okay, so any other questions? I hope I could make some sense about this SVMs. So the Lagrangian part, I understand that it's a bit shady, but I'll try to give. I don't think I will be able to give any intuition, but I'll try next class. Yeah.
Sir, we are not expecting answer of last in assignment, but could you elaborate sigmoid function that in, because I am finding definitions are closer to that. Sigmoid I familiar, but in the last the current assignment in the last question.
Oh, that we are not allowed to solve. I have not looked at that question.
No, I am not asking the answer also, but could you elaborate like gradient descent one that because learning rate are defined like also 0 to 1 probability, but in that context, because lots of where sigmoid function are used in different contexts.
So I actually did not look at the question. So if you can tell me what the question is, maybe I will give you some idea.
Our question is what is the sigmoid function role in logistic regression? That options are I will solve my own question, but let me state here. The sigmoid function transform the input features into the higher dimensional space. Second is sigmoid function calculates the dot product of input features and weights. Third option is sigmoid of function defines the learning rate of gradient descent, and the sigmoid function, the fourth one is sigmoid function maps the linear combination of feature into probability values. So the last one is that like a little confusing, like ultimately it's a map 0 to 1 probability distribution, we can say, but
okay, so okay,
I'm
can't
not
give
expecting the answer, but just the what it like a little bit sigmoid function in this context, logistics.
Right.
Regression.
So yeah. So So as I said, for
function for my okay.
So W transpose X plus B is common in all models. So for classification, what you need to do is you need to find out that when this is class 1 and when this is class 0. That is your
binary.
For binary classification, that is your solution. I mean, that is the thing that you are after in classification setting. So so you need something to say that okay, W transpose X plus B has to either be 0 or be 1. So that is your final motivation. So
we are just using as a sigmoid function mapping to 0 to 1
yes,
of this value as an input z.
Yes,
Suppose we say it as z
yes.
and sigmoid.
So sigmoid, so as I said here, if it is greater than 0.5 we will say it is positive, if it is less than 0.5 if we will say it to be negative. So that is the only role of sigmoid function. So any other role if it has, then you need to see it for yourself.
Okay. Okay, thank you.
Yeah.
Basically,
where we can get more detail if wanted to interested that from mathematical any book or reference you could suggest in a brief, not in detail actually. Which book so we can refer like for reference to more reading or detail?
Yeah, so there is one book called Hasty Tipshirani. I've forgotten the name. I think it's Elements of Statistical Learning or something. So this is a good book for starters, and there are two more books. One is Probabilistic Machine Learning by Kevin Murphy, but that is a slightly advanced book. So that is one. There is also Tom Mitchell's book on machine learning.
Yes, that is it.
And there is one more book, Christopher Bishop. These four books, I mean, the first book is, I think, the best for starters at least. For SVMs at least, you can refer to Bishop. I don't know about the other two because I have not looked at them, but Bishop.
Yes, actually, I am asking for the SVM context.
So SVM is very good in Christopher Bishop. The one thing that you have to understand is for SVM, you would also need to refer to the appendix of each book, because all those optimization things that is there in SVM will be there in appendix. They will not be there in the main chapter. And that will I would also suggest that you need not go through that as of now. When you have some leisure time, you can go through.
Yes, definitely.
Because it will distract you from the actual path of this course. That's what I believe. Okay, so yeah. So any more questions?
Just one query. In the there in the stack variable they mentioned slack variable, and they denote it with the C. Generally, slack variable is zeta.
No, slack variable is always slack variable is always zeta.
Zeta. In the question, that's why I get confused. They are denoting with the C.
Then if that is mentioned, then that is wrong. Slack variable is always zeta.
So in question, we have to C take as a parameter, and zeta will be that
slack variable. Yes.
Okay, thank you.
Okay, so if there are no more questions, I'll close the session, and I'll again next Tuesday, same time.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Today's session was very good, sir. I mean, we had a lot of doubts in this SVM. Most of it was clarified. Thank you.
Thank you. Thank you. Good to know that I could help. Thank you. I'll close the call.